All right. What did we do in chapter 1? Vocabulary. It's pretty much, we learned about what a research is, what a study is, what all these and how do you put it together. But we never talked about any numbers or anything. We did talk about the more subjects you have in your study, the more accurate it becomes. Okay, so now let's pretend we have a study. We know what we're going to look for, and we're collecting data. What do we do with that data? Because think about it, here's the drawback. The more data you have, the more stuff you have to work with. And you guys are lucky because now you have something called Excel or Qualtrics that will take this information and put it in a spreadsheet for you already. The way we had to do it in the past was we'd get 400 or 500 or 600 pieces of information. We have to enter it all manually into our database and work from there. Now, once we get all the data, we have to do what with it? What would you do first? Once you collect the data, what would you do with it first? Organize it. Yeah, because by itself, it's just data. It doesn't become information until we process it, fix it up, clean it up, and do something with it. The first thing we're going to talk about is organizing the data via frequency. What do you think frequency, just by the word of it, frequency distribution? What do you think that means? Yeah, try to do this without reading the paper. Because I want to see what you know already. Just by the name, frequency. What does frequency mean? What's that? How often? Yeah, you're right. It's distribution. What is a distribution? Spread out. Exactly. So we want to see how these numbers are spread out. If we had small set of numbers, let's say 10 numbers, do we need to worry about organizing them? You say yes. Porque yes? You say yes? Yes, it's always, always, always important to organize your data. For one, you'll be able to see patterns forming already. And then two, not everything is numerically based on the numbers themselves. We're later going to talk about something called the mean, median, and mode. Have you heard those words before? What do they mean? What does mean mean? Average. How do you find the average? How do you find the average? And exactly. So the average is you add up all your data, all the numbers you have, and divide by how many you have. Like for your test, for your grade for your school, your homework average. Add up all your homework, divide by how many you have, and that's your homework average. What does median mean? Very good. Think of that thing you hit when you make a turn on the road. That's that thing in the middle, that concrete thing as your tire hits. That's the median because it's in the middle of the road. What's mode? Give me an example of why it's called a mode. Where is it used in the real world? Yes, the mode is the most frequent. Think of fashion. When everybody asks, how is everybody dressing now? What they call that is, what is the mode du jour? What is the current dress? I mean, have you all used to always wore blue jeans with holes that you could stick a car through? No. What happened is somebody from Hollywood was paid to wear something like that. And all of a sudden everybody saw it and they wear it that way. Think of the way when you wear sweaters. How many of y'all tuck the front end so you see the belt buckle and let the rest of the sweater hang out? That's the mode du jour. I can't stand it. I mean, either let it hang out or tuck it on your pants. Don't do both. But yeah, that's what that mode stands for, is the most frequent. What is everybody wearing now? But not all of those depend on the specific numbers. We just look at how they're scattered out. But let's first look at this. Well, we're going to look at the chapter problem is traffic. Stuck in traffic. The frequency distribution shows how data are partitioned in your data set. Categories or classes. What do you think those are? What are categories and classes?
Sections to divide the data.
Yes. The different, like in this example here, we have traffic. Right now, by themselves, that means nothing to us. So we have to do something with that. How many pieces of data are there if you just look at it? No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 times 3 is 45. And then there's 50 of them. And that's a very small data set. How do we organize this data?
The smallest commute time to the largest.
Okay, true. So we put it in the slowest commute time to the largest. If we do that, we'll have how many categories? 50, because each one will be their own category. So if we only had like 10 or 12 or 15 pieces of data, that'd be perfect. But once you have this many, anything more than, let's say, 15 or 20, you want to put them in what's called a frequency distribution. You want to break them up into classes. So we have to break our data set into groups because right now by itself, we can't do anything with it. So since we know our numbers go from 5 to 90, right? How many intervals do you want? How many classes do you want this thing to be spread out about? If it's too few, then it doesn't tell us much. If it's too many, then you water it down. So for this, N represents the number of classes. Let's say we have 7 classes. I want to have 7 distinct classes. 1, 2, 3, 4, 5, 6, 7. So how do I arrange them? Where do I go? The classes are intervals. How big are the intervals going to be? The next question is, first question you ask yourself, how many classes or intervals do I want? That's the first thing. We said 7. Next, we have to find the class size. How wide are each of these classes going to be? Yes. They each have to be the same. In other words, if it's, if you think of it from 0 to 9, that's 10 numbers. Then you go from 10 to 19, 20 to 29, and so on and so forth. Always has to be the same size. If not, then the frequency will be altered and it's not going to be uniform.
You start with 0, or you start with.
That's a good question. That's a good question. That's the next thing we have to talk about. But first, let's figure out the class size. How do we figure out the class size? We first have to figure out how far is it from the smallest to large. Yeah, it was. How far is it from the smallest to the largest? How do we find that? How do you find how many numbers are the numbers between the smallest and largest? How do you find that?
1 times 5,
Why?
smallest and largest.
Yeah. Take the largest minus the smallest value. So that gives us the range of the data set. So now we know how far it is from the smallest to the largest. Now what we have to do is, since we know that, we divide by the number of classes we want. So we have, what's our smallest? Looking at this list, what's our smallest? 5. What's the largest? And how many classes do we want? 7. So 90 minus 5 is 85. Divided by 7. 12 point something. Just 12 makes it 84. So it's one left over. So it's approximately 12.2 or 12.1. But 12 is a weird number. So we can, at this time, we could round it up to 13, or we can make it even bigger and make it 15 or 20. You can control it that way. But if you make it too big, remember, your outer bands may be too small. So let's raise this one to 15. Again, you have total control. You could round it up to 13 if you want to. You can round it up to 17, 18, whatever. So 15 is just an easy number because it ends in a 5. So the third thing we do, we know how big each class is going to be. So that means in each of these classes, there are going to be 15 numbers. At this point, you look at what's the smallest number that you can have in the data set. What is the smallest number you can get?
5.
No, that's what it is. But before you started this, what is the smallest that you can get? 0. Because it just so happens that they got these numbers by watching the traffic. What if there was a vacation and nobody drove that day? So it is possible to start off at 0. So 0 to what number would give me 15 numbers? It'd be 14. Think of this. Between 0 and 9 is how many numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So whenever you start at 0, always add 1 to the end, and that tells you how many numbers there are in that group. So that's my first set. Now from here, I can use 15 because each of my beginning numbers will be 15 away. 0 plus 15 is 15. 15 plus 15 is 30 plus 15. 45 plus 15. 60 plus 15. 75 plus 15. So that's my lower end. That's my lower bound of each class. Now, basically, for these endpoints, all we have to do is, since this one's 30, this one has to be what? 29. This one's 45, so this one has to be 44. How far is it from 14 to 29? 15. So from the beginning, add 15, from the end, add 15. So that's how you get now you have the class size. What you have to do now is look at the data set that you have and tell me how many numbers go in each one. So go ahead and do that for me. Actually, on the second page, you can make sure you fill those in when you finish. On the top of the second page. So this is your data set. It's in the first page of your sheet. Yeah, so you don't have to flip back and forth. Write the frequencies on your piece of paper, on your scratch paper in your notes. So you don't have to flip back and forth, back and forth, back and forth. You can do it. I want you, with this data, tell me how many are in each one of these classes. Yeah,
I was doing that.
yeah, but instead of flipping back and forth, just get a piece of paper and you write it there, or on.
So you're just gonna leave it up there, that's why.
Well, I'm going to leave this up there. Oh, I see what you're saying.
Yeah.
Yeah, but then that's going to give you a headache. I said you came in late. I saw you just copying them, the class sizes, these numbers here. It's where we got those is what's important. We got them from this formula. The class size. This tells us the class size is the width. So start with the largest number in your data set minus the smallest. And divide by how many classes, how many intervals do you want? We said 7, so we divide by 7. You could have chose 10 if you wanted to, or 5. So then once we got that, 12 point something was not a good number, so we rounded up to the next. The reason 15, anything that ends in a 5 or 0 is good is because it's easy to add there. 5, 10, 15, 20, 25, 30, or 10, 20, 30. So if always try to make it end in a 5, it makes it much easier for you. And then the smallest possible number you can get on your data set could be 0. So now you add 15, from 0 to 14 is 15 numbers. And then, so for this beginning next one, 0 plus 15 is 15, 15 plus 15 is 30, plus 15 plus 15, and we do both ends. That's how we build our intervals. Now we got to fill in the blanks and how many of each number we have. So here, I'm going to let the cat out of the bag when I wrote this up there already. So you have your intervals, your classes. What you have to do here is look at through the data. Anytime we see a number between 0 and 14, put a mark there. That's what a tally is. So let's see in the first row, are there anything between 0 and 14? There's an 8. There's a 10. There's a 10. Second row. Third row. So how many of them are there? This way is the best way of doing it. Why? Because how many times have I interrupted you guys trying to do your work already? About 5 or 6 times. So if you did it the way you guys were doing, or counting and stuff like that, you won't know exactly where you left off. This way, if I stop, I know where I am already. I went through the 6 numbers that are between 0 and 14. I count 6. If there are any more, I'm done. How many between 15 and 29? There's an 18, 25, 25, 25, 20, 20, 20, 15, 15, 20, 15, 25, 25, 15, 20, 25, 25. So how many of them are there? Yeah, well, 5, 10, 15, 16, 17. What's that? That's time marks, yeah. It makes it much easier to look at that way. Yes. Well, so I did here, now between 15 and 29. I start with the first one. Is this number between 15 and 29? Yes. So I put a mark there. Yeah, but I'm looking for numbers between 15 and 29. Well, from 15 to 29, including 15 and 29. So 18 is between there. 25. Well, let me restart these. So I have 15, 25, 25, 15, 25, 20, 20, 20, 15, 15, 20, 15, 25, 25, 15, 20, 25, 25. 18. Okay, now that's one way of doing it. Can you think of a better way of doing it? There's a better way than that. Instead of looking individually in each group, put this again. Same concept. So we have between 0 and 14, 15 and 29, 30 and 44, 45 and 59, 60 and 74, 75, 89, 90 to 105. Now, here's a better way of doing it. It's also using tally. But instead of looking for individually class, look at the first data. 18. Where does it belong? So there. The next one, 25. Where does that belong? The third one is 45. It belongs here. Then 75. Then 60. Why is this a better way? Because now if I stop, I know exactly where I left off. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm now here. So the next one is 40 and 25. 40 and 25. And keep on looking at your list. 8, 50, 10, 10, 30, 15, 25, 50. So this is the easiest way of doing it. Use your entire chart and go one by one and just tally mark. That way I know exactly where I left off. Because all the other ways, if you get interrupted or anything like that, then you have to start over again. So now I'm on the second row. 20, 30, 20, 45, 30, 60, 30, 20, 15, 30, 60, 30, 15, 35, 40. That's the second row. 5, 30, 40, 20, 10, 45, 30, 15, 25, 25, 5, 90, 30, 15, 60. 20, 60, 30, 25, 25. So now I could do what? Just count how many marks I have. I got 6 here, 18 there, 14 there, 5, 5, 1, and 1. How do we know that's correct? Yeah, so that's the only thing we're taking an assumption. Do we know we have all the data? Right. If you add up all the frequencies, 16 plus 14 is 20, 30, 48, 49, 50. Yep, we're supposed to have 50 pieces of data. And we know our lower class limits and our upper class limit. So far, so good. Yeah, see, but the upper class is actually, it really doesn't matter. I can put 110 if I want to there, but it just, it encompasses everything. So what have we done so far? We've collected the data. We've now organized it. How is this organizing the data? Yeah. So I know I have 6 numbers there in this small group, 18, 14. So what does 18 represent? Is it a mode? No. What is a mode? Mode is the most frequently occurring. Most frequently occurring. So the biggest frequency is that one. But it can't be the mode. Mode is singular. This is the biggest frequency. It belongs to this class. So, but that class is the modal class. In fashion, they do the same thing there is, what is the most popular size in men's and women's clothing? Why do they need to know that? To see how much they have to make and then sell to all the companies. So if the middle size, let's say for men is 34, they know they have to make a lot of those. And not only that, but since that's the most frequently occurring size, they can make those the more expensive pants. That's how we look at clothes, and it's exactly the same clothes, just different sizes. They cost different prices because supply demand. Now, with these, we're gonna start doing some calculations in a little while. This is interesting. Let's look at this part about no phones or bathtubs. Many statistical analysts must consider the changing characteristics of the population over time. This is page 3. Here are some observations of life in the United States from 100 years ago to today. From 100 years ago, 8% of the houses had telephones. How many now? No, they don't have phones. People got rid of their phones because they have cell phones now. You don't have home phones anymore, or not everybody does. Everybody used to have a home, at least one phone line. And if you did business, you had a fax machine also that had another line. But you don't have those anymore because your computer does everything now. Oh God, they wouldn't know how to use a fax or a telephone. 14% of the homes had a bathtub. Wow, 14%. Actually, that's interesting now because a lot of people don't like bathtubs. They're just more things you have to clean. So they get rid of their bathtubs and just have a big walk-in shower. The mean life of expectancy 100 years ago was 47 years of age. Why is that? Possibly a very good thing, yeah. I mean, think about it. If you don't brush your teeth and you just eat whatever you can, the sugars in there will do what to your teeth? Will make it rot away. You'll fall apart. So you can't eat anymore. And you get weaker and weaker, and then ciao. But more so than that, think of how it was 100 years ago. Did they have Walmarts back then? At best, you had a general store. And they didn't have everything because they had to have the food and everything for that whole city. So you couldn't get everything you wanted. Do they have everything preserved? You can buy a loaf of bread now, it can last a couple of weeks. A gallon of milk can last a couple of months. But back then, how long could something last?
2 days.
At best, yeah, if you had meat, you better eat it up now. Because refrigerators really weren't that popular back then. The mean hourly wage was 22 cents an hour. 22 cents. What is it today? Almost $20 an hour. It's like $18 an hour. But if you think about that, $18 an hour and a full year salary with that amount would be $36,000 a year. What about them? 22 cents an hour. You practically work 2,000 hours a year. That's the rough estimate, 2,000 hours a year. So if you work for us, let's say 50 cents an hour, how much money did you make for a year if you worked for 2,000 hours? 50 cents, half of that, so it's $1,000 a year. Divided by 12, that tells you how much you make per month. Yeah, so it's not that, and that's within 100 years. There were approximately 230 annual murders in the entire United States. Well, guess what? Here we are in end of January. Dallas is there already. Just the city of Dallas. How times have changed. The population changes, the cultural aspect of the people changes, everything. So yeah, and I know you hear it all the time from your parents, your grandparents like that. And what the older generation tells you all, trust me, in about 15, 20 years, you'll be saying the same thing to your kids. You say, when I was a kid, we didn't do that. Well, when you were a kid, we spent all our time on our cell phones. When your parents were kids, what did they do during the day?
Go outside, let it be.
Go outside and ride a bike, climb a tree, play baseball. Your great grandparents, what do they do? Chase dinosaurs? No. Yeah. Yeah, who had to work because they had to grow their own food. So how times have changed. Think about what life's going to be like. The job you'll get and you retire with right now hasn't been invented yet. Most of y'all. That's super interesting. The jobs that you're going to be getting when you graduate college haven't been invented yet. They're still in the planning process. Example 1 on page 4. Using daily commute times in Los Angeles. Oh, we did that already. That's a class with. What do you think? What is a categorical data? Just by the name of it, what do you think categorical data is?
Data that is categorized, like what we were doing previously, similar to it.
What? Because the time intervals are not really, they are categories, but more so now in categorical, we're looking at specific characteristics. On Monday, if you look at Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, is the way you dress, does it change during the week? What influences that?
My tiredness, I'm lazy.
Yeah, so on Monday you dress better. Or is it Tuesday, Wednesday you dress better?
Think I'm so tired.
But Friday and Saturday, how do y'all dress? In the morning, you you just roll out. But yeah, and evening time, afternoon, you got to do stuff, so you dress up nice. Sunday, you go to church, if you go to church. In the morning, you're great, then the afternoon, you get back being comfortable. Monday, you're tired? Or are you energized? Yeah, a lot of people are tired. They're thinking, oh, it's Mondays, beginning of the school week or a work week. So they're not too energized. Then when you get to Tuesday, Wednesday, now you're at hump day. So I'm really excited. So the dress starts getting better towards the end of the week because after work, they go out and do stuff. So yeah, so these categories, for in this example here, the causes of plane crashes. What do you think the causes of plane crashes are? How many can we think of? Look, we'll call that pilot error. Pilot error. Because the pilot's responsible to check the airplane before they even start the engine. Weather, that's a big one. What else? It says, what could cause an airplane to crash? Yeah, malfunction, some mechanical error. And there's the pilot, when we get to the airplane, we look at the airplane, and let's look at the engine. We just look at the outside. Is there any oil dripping? Is there any gasoline dripping? Are there any wires disconnected? Then we close it back up and get inside the airplane. But you can't see inside the engine. You check the oil, yes, you check the gasoline. I mean, you check everything in gasoline. You check to see how much water is inside the gasoline. Because the more water you have in a gasoline in an airplane, the less you're going to fly. You'll crash much faster. So then the mechanical is stuff you can't see inside the airplane. You can't see the wires that control the flaps and the ailerons. What else can go bad? What are we in passenger? Yes. Either they have a bomb or something, and they're going to ruin your flight. Or if you have a disgruntled employee who you got fired and they used to be a mechanic, they go in there and clip some wires that you won't know until you took off. And what else you can cause it? Wouldn't that be mechanical? Yeah.
I don't know what it's called, but
That's what you're saying with electronics, with mechanics.
something similar to that. You know how like they can see the plane on the screen, so they make sure not to crash into them. And
The towers.
yeah.
Well, yeah, that's another one is the. But then is it the tower's fault? Yeah, actually, the tower gives a clearance and tells the pilot when they come in for a landing exactly what altitude, what speed, and everything. And your mechanicals in there tell you, it's amazing. If you ever get a chance to learn how to fly. Is the technology nowadays. First off, an airplane can taxi from Dallas, take off, land in Frankfurt in Germany, and taxi without the pilot touching anything. It's that automated. The pilot just sits there in case anything breaks. But no, everything. I mean, when you drive in fog, do you drive fast or slow?
No.
Very slow, right? Do you put your high beams on? Don't. Because what is fog? Fog is water. Actually, what it is, it's actually a cloud. The pressure of the cloud, it's water molecules that are just suspended in air. When you turn your high beams on, you're illuminating all of those water molecules. That's why it becomes super bright when you turn it on. So don't put your high beams on, put your low beams on. You'll see much further. A lot of countries in the world use yellow lights, like France. Yellow lights are the best when it comes to fog. You can see dozens and dozens of yards ahead with yellow lights. But never use high beams. Leave it at low beams and slow down. You'll see a lot better. But the tower, airplanes, you don't even have to see the airport. Your dials and gauges will tell you what line you're supposed to be in, what altitude you're supposed to be in, and then what speed you're supposed to, and it'll put you down at the end of that runway. Just follow your instruments. It's just that the hardest part is the first time when you start doing that, you can't see outside the cockpit, and you have to trust what you see. It takes about a year to get over that fear of, I'm not gonna trust that. If I can't see it, I don't believe it. Well, if you can't see it and you're flying and you can't see anything, what's gonna happen? You'll run out of gas eventually. So can you slow down when you're in an airplane like you can in a car? Nope, you have to keep a certain speed to stay above the air. Anything below that, it stalls and you sink like a rock. So these are possibilities. So let's look at this. These are the causes. These are the frequencies. So let's say from the FAA report, we have this. Pilot error, we have 640. Mechanical, we have 195. Weather, we have 63. Sabotage, we have 95. Everything else is the FAA. Those are what have been recorded from 1960 to now. How many of y'all watched the news last night? What happened in Washington, D.C. last night? What's that? More than crash. It hit a Black Hawk helicopter, it hit a military helicopter. Exactly. How can that happen? Because the military is supposed to have all these gauges and instruments if anything's getting near them. And these aircrafts have these collision avoidance systems that will tell you, watch out, there's something in front of you, move up, pull down. But how can that happen? And that's what we're going to find out. But when it comes to final approach, landing and taking off is the most dangerous time in an airplane. Because when you're landing, you're at just above the speed of dropping out of the air. Because you want to go as slow as you can when you hit that runway that you can stop by the end of it. So one of the aircrafts were coming in for a landing. The other one must have been going across. And then they collided. And then they landed in the cold Potomac River. So yeah, that's sad. But again, how? How can this happen? And the tower should see if two things are crossing. So unfortunately, again, that happens. With respect to frequency, again, is what? The number of times it repeats. We have two types of frequencies. We have relative frequency and cumulative frequency. Relative frequency is just that. It's relative to the entire data set. So the formula for relative frequency so I'm looking at the class frequency divided by the sum of all frequencies. So let's look at our example. Here's my classes. Here's my frequency. I want to know the relative frequency of each class. So I'm going from 0 to 14. I have 6. 15 to 29. I have 18. 30 to 44. I have 14. 45 to 59. I have 5. 60 to 74. I have 5. 75 to 89. I have 1. And then from 90 to 104, I have 1. So what would be my relative frequency? To find the relative frequency, what do I need? Do we have the class frequency? Yeah, that's that. This is the class frequency. Do we have the sum of all frequencies? Yeah, we add up all these, we got what? 50. So this one's going to be 6 divided by 50. Let's see if we have those in there. That's roughly about 0.12. Next one is 18 over 50, approximately 0.36. It's going to be more than that, so round your decimals into 2 decimal places. Then we have 14 divided by 50. That equals 0.28. 5 divided by 50 is 0.10. 0.10. 1 divided by 50 equals 0.02. 1 divided by 50 is 0.02. Checks and balance is a beautiful thing to keep you from going astray. We knew when we look at the class frequencies, if we add them all, we better come up with how many data points we have. Check. How do we check this one? How do we check relative frequency? If we add them up, does it equal 100? .12 plus 0.36 plus 0.28. Does that equal 100? It equals to 1. It has to equal 1.0. The reason for this, I'll show you. Because these next two are going to be how they're related. Now, as a percent, the relative frequency as a percent. How do you find a percent? Yeah. Part over total times 100. That's a percent. So here's the part over total. We did that in the relative frequency column. So we just multiply each of these by 100. That'll give us 12%, 36%, 28%, 10%, 10%, 2%, and 2%. If we add up all those, how many do we get? We should get 100% because 1.0 is the same thing as 100%. Pretty straightforward. So the frequency of each class is just how many each one. The relative frequency is take that number divided by if we add them all up and then multiply by 100. The third frequency we talk about is the cumulative frequency. Cumulative simply means it refers to a running total. How do we find the cumulative frequency? We only look at the frequency class, the class frequency. And all you're doing is, we'll start with this first one. It starts at 6. It tells us at each level, how many pieces of information do we have? So we have 6 in the first one. We have 18 more. So how many do we have so far? 24. Because we have these 6 and these 18. Now we have 24. Now we have 14 more. That's 38. So we take this number and add this one to it, equals 24 plus 18. 24 plus 18. That's 30, it's 52. Oh, no, it's a frequency. It's the frequency. Yeah, it's 42. No. 6 plus 18 is 24. Oh, that's where I messed up. This one's on the wrong row. This one's in the wrong row. But okay, so the first one is 6. This is my frequency. I have 6. 6 plus 18 is 24. 24 plus 14, 38. 38 plus 5, 43. 43 plus 5, 48. 48 plus 1, 49 plus 1. This is the number we're looking for. Because it has to match that number. If it doesn't match that, then we did something wrong. Now, can we use these frequencies for anything? Can we use relative frequency or percent for anything? Remember, there's a reason, there's a purpose you collected the data. What does this data represent? The number daily commute time in Los Angeles. So this is how long it takes to commute. So what's the most common commute time? Yeah, between 15 and 30 minutes takes you to drive in LA. That's the majority. But then the people who talk about these, that takes forever to drive, there's only couple of those. So that's how you use these things. So 36% of the people only have to drive within that class time, that amount of time. How do we know our data is valid or we can do stuff with it? Because if it's broken up in a bunch of pieces, we can't do anything with it, really. We're going to use this term a lot in this course. The normal distribution. Have you ever heard normal distribution before? You've heard of its commonly known name. How about bell curve? You've never heard of bell curve? Wow. Remember what we said earlier about 8% of the people had bathrooms in their house? This is bell curves. There are some instances where teachers grade on a bell curve. When I was in law school, the exams there are graded on a bell curve, which means this: a bell curve looks like this. That means it's normally distributed, which tells us this. This is our mean, the middle number. We know that 50% exists on both halves. So think of grades. This marks 50 as a grade. If the 0 is the smallest and 100 is the largest, that's how your grade should be distributed. I'm not going to go too much into this part because we're going to talk about it further later on. We could break it up into smaller categories where this percent gets an A, this percent gets a B, this percent gets a C, this percent gets a D, and everybody on this half gets an F. That's how grades are distributed. So according to this one, if this was 50 and that's 100, we could say something like this is 90, 80, 65. We make distributions like that. So if you scored between a 50 and a 65 in that class, you have a grade of D. If you scored above a 90, you made an A. So that's how good. Now, is this fair? No. Why not?
It's not based on making an 80, it's based on where you fall in the.
Well, that's what it is now. If you make an 89 or if you make an 80.0, what's your final grade in the course? B. There is no distinction on B in which gradated scale. So same as in here. So as long as you fall in here, you get a B. No, the reason it's not fair. What if all of you guys were super smart students? Because remember, this goes with the grade range. The lowest grade at the highest grade. What if the lowest grade in the class was a 90 and the highest was 100? What's the middle grade there? So anybody who makes a 90 to 95 failed the course. This could be 96, 97, 98. So in order to make an A in the course, you have to make an average of 98 or higher. That is how professional schools are. That's how law school was. The instructors would put the lowest score and the highest score, do the bell curve, and wherever you fell, that's your grade for the course. Well, it sucks. And the way they do it in law school is at the end of the semester, the instructors would post all their grades on a board. They call it the wailing wall. Because literally, you can hear people scream and cry from outside the building. Because they look at the score, if they fail, they know their career is over as a lawyer. You get kicked out of school if you fail a course. Yes, and you can hear people, remember, just get to the law school or medical school, you have to be the best of the best to begin with. You already have to be an A+ student to get that far. Now, making a isn't good enough anymore. You have to make an A+ to barely pass the course. And we're going to talk about bell curves later on in extent, a lot of discussions about it. When you do your data, What if you saw this in your data? If you saw this, the frequency, a big number, zero, big number, zero, big number, what would you think about that? What this represents is the pulse rate of people. What nurses record. The digits of pulse rates from the National Health and Examination Survey. The, why not? Have you ever, when you get your blood pressure read, what numbers do you usually hear? 120/80, 94/60. It's usually always uneven numbers. For some reason, they don't like odd numbers. So that's what they're saying here, their pulse rate. And very rarely, and the way they do it to figure out how fast your heart's beating, your pulse rate, feel your pulse for 15 seconds and then multiply by 4, because that's how many seconds in a minute. 15 times 4 is 60 seconds. So that's how you figure out how many times your heart beats a minute. So when you take a number and you multiply by 4, what happens to that number? Think about it. 13 times 4 equals what? Let's see. 13 times 4. 4 times 3 is 12. 52. 15 times 4. 60. Can it ever end when you multiply by an even number, it always comes out even. So that's in your medical records, you'll always have an even pulse rate for your heart. Because why? Nobody wants to put their hand on yours for 1 minute and count. So they just hold it for 15 seconds, multiply by 4, and I'm done. Move on. So when you notice something like that, when you notice gaps in there, then be very careful. Try to understand what's causing that gap. Example 5. Let's look at this one. This is our last example. What's here? Gaps. The presence of gaps can suggest that the data from 2 or more different populations. What does that mean? In medical field, populations can be male, female, or experienced, unexperienced, or nurses using technology and not using technology. Because they have things now they can put it on your arm. It'll give you all the information you need. How much oxygen your blood has. It'll calculate everything. So example 5. Examination of the frequencies, this is the frequency distribution of the weight, grams of randomly selected pennies. Do you ever think about pennies? How many people ever deal with pennies anymore? A lot of people, when they see pennies, what do they do with it? Get rid of it. No, I think it's ridiculous. I could walk around a parking lot and literally pick up 50, 60 cents a day. After a couple of days, I have enough for a drink. People just throw away free money, which really burns me up. But people don't use. What are pennies made up of? They used to be. Because copper got to be super expensive, they thought of other things to put in there. So that's what this is all about. The frequency distribution, the weight, randomly selected pennies. Examining the frequencies reveals a large gap between the pennies. This suggests that we have the following populations. Pennies made before 1983 are 95% copper, 5% zinc. Pennies after 1983 are 2.5% copper and 97.5% zinc. Why? Because copper is very valuable. You use copper in your refrigerator, your AC unit. It's the coils that takes that hot air and pushes it out into the environment as sweat. So this is what happens. This is when you weigh these, because you know how they're made up now. If it's made before 93, it's made of this. So can we tell this because it's made up of this, all copper weighs the same and all zinc weighs the same, supposedly. So if you weighed the pennies and this is what they weigh, between 2.4 and 2.49 grams. So if you look at this, these two are pretty close to each other, from 2.4 to 2.6 grams. 0.2 grams difference. That's very light. The other end of the spectrum, this one I wouldn't even worry about, really. There's only two of them. But the majority of them are from 3 to 3.2. So simply by weighing the pennies, you can see what the year of it is going to be. So the heavier the penny, what's it going to be? Is it going to be before 1983 or after 1983? Which is heavier, copper or zinc? Copper. So if it's heavy, it's going to be an older penny. Actually, you ever see any movies of the Old West where they took the coin and bent and bit into it? You ever see any of that? What they're doing there is seeing how much gold is in that coin. Why? If it bends easy, how you think it's a lot of gold or not a lot of gold? Wrong. Gold is very malleable. If it bends easily, it's a lot of gold. If it's solid, it's anything else but gold. It's like copper or zinc or iron. So yeah, it's just the opposite, because when you pick up gold, it's super heavy. But when you put it into a coin, you can bend it and break it. All right, so that's what this section was about, was frequency, relative frequency, and cumulative frequency distributions. Next time, we're going to look at graphing them. We're going to look at, oops. Oh, did everybody get a copy of those notes? Yeah, next time we're going to look at graphs. The title of the section is Graphs That Enlighten and Deceive. Because you can't believe the graphs you're looking at. All right, have a great day, everybody. Enjoy the sunlight while it lasts. And we'll see you guys